Hello, this is Math 2270 coming to you from the College of DuPage for the summer of 2020, and this is the conclusion of the lecture on mechanical. As we mentioned in the introduction of this chapter, many different physical systems can be described by a linear second-order differential equation very similar to the differential equation of forced motion with damping. And that's what you see here shown as 32, and we studied the heck out of that. If I of t denotes the current, which comes in amps, in the LCR circuit, L stands for inductance, R is resistance, and C is capacitance, series circuit shown in the figure over here, then the voltage drops across the inductor, resistor, and capacitor are shown I guess I didn't copy the figure, but anyway, if you use Kirchhoff's laws, you get that this is the representation you get. So you see things match up very well, although we're using different letters. But the charge, Q of t, on a capacitor is related to the current by I is equal to dq dt. The change in charge per unit time is the current is an amp, and so and charge comes in coulombs. So this could become, if we make that substitution, this becomes a second order differential equation. You can see that it matches up very nicely with number 32. The nomenclature used in the analysis of circuits is similar to that used to describe springs and masses. We talk about electrical vibrations, and if that's equal to 0, the circuit is said to be free. There's an auxiliary equation that's a quadratic, and there will be three forms of this depending on what the discriminant is. It can be overdamped, critically damped, or underdamped. In each of these cases, the general solution contains the factor e to the minus rt over 2l, so it goes to 0 as t goes to infinity. That's a transient solution. Many of the things are the same. When there is an impressed voltage that's said to be forced, and we talked about transient solutions, and the particular solution becomes the steady state solution that exists over time. Well, here's a problem for us to do then. Find the steady state charge and the steady state current in an LCR series circuit when L is equal to 1 Henry. Henry is the unit of inductance. R is 2 ohms. C is 0.25 farad. That's named after Michael Faraday. And the electromotive force is, and this is alternating current because it goes, it oscillates like a sine, 50 cosine of t volts. You know what to do. Let's see how you did. Well, if you work through that and translate things correctly, you end up with this being the homogeneous differential equation that you're solving, and this is the complementary solution. Now again, notice that this is e to the minus t, so that's going to go to 0 over time. The steady state charge has the form, and we're looking at the other side, and that is going to be, you can annihilate it and then substitute this into the original equation. A cosine t plus b sine t. If you substitute and do the algebra, and I encourage you really to do this algebra because one day I would ask you to do this kind of algebra, you get this. And you will say that this coefficient of the cosine will be 50, the other one will be 0, and you solve that system of equations. You get A is this number and B is this number. Now that means that the steady state charge is this. And if I take the derivative of that, I will get this, and that is the steady state current. Recall that they ask us for both of these in this problem. Let's look at another problem. Find the steady state current in an LCR circuit where L is 1/2 Henry and you have all of these numbers. Note that C is a very small number of farads. And here you have kind of a complicated electromotive force because you have something operating at 60 cycles a second, something else operating at 40 cycles per second with different amplitudes. But anyway, it's just a differential equation. You know what to do. Let's see how you did. So this is the one that this is what you would set up for the second order differential equation. This would be your complementary solution, and that goes to that's your complementary solution to that. And notice that you do have the C1s and so on and so forth. But I think they just ask you for the steady state solution. So what we're looking at is we're annihilating the right hand side. We have a solution that looks like this. We plug it into the original equation, do a lot of algebra, and we solve an equation, 4 equations in, 4 unknowns. A lot of work, but you know how to do this. We get these are the coefficients for A, B, C, and D. So the steady state charge is going to be this, just using those coefficients. And the steady state current is the derivative of that. And we take the derivatives and we have that. I think the problem was asking us for the steady state current. I'm not really sure. Okay, so we can solve problems like this. They're the same exact and there are many examples of this. This is a mechanical engineering thing dealing with a twisted shaft and the differential equation governing the torsional motion of the weight suspended at the end of the elastic shaft is given by this differential equation. If you look at it for a while, you say, wow, that's really the same differential equation. This is showing you what theta is in that case. So you see you have mechanical vibrations, you have different kinds of torsion vibrations, you have electrical vibrations, and you even have models for the simple pendulum that although this is very nonlinear because of the sign of theta, we know that for theta being small, sine of theta is almost theta, and this is exactly the kind of differential equation that we've been solving, so that could be an approximation for that. To solve this, really, what you have to do is you have to do an infinite series. This is the infinite series for the sine. Now, the reason they can get away with this approximation is if theta is a very small number, theta cubed is even smaller, and theta to the fifth is even smaller. So they ignore those. This is actually an excellent lead-in to our next topic, which is going to be infinite series. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and each other. God bless you all.